Question number 1. A solenoid is made from a 10-meter length of wire. This wire is wrapped in a cylinder that is 8 millimeters across and 20 centimeters long. If 100 milliamperes is run through the solenoid, what is the inductance of this solenoid? Please pause the video and attempt the problem. So this problem, we can solve it with a basic plug and chug. We have the formula L is equal to mu sub naught N squared over L times A. And again, remember these two L's are different. This is the inductance, and this is the length of the solenoid. So mu sub naught is a constant. That's that 4 pi times 10 to the negative 7th Tesla meters per ampere. To find N, we take the fact that the wire is in total 10 meters. And if the solenoid has a diameter of 8 millimeters, and it has a circumference of 0.025 meters. So 10 meters of wire divided by 0.025 meters of wire per loop gives us 400 loops. So N is 400 loops. We can also say that with an 8 millimeter diameter, the cross-sectional area is given by pi r squared. 8 millimeter diameter means 4 millimeter radius, and so the cross-sectional area of this inductor is 5.03 times 10 to the negative 5th meters squared. Finally, length. The length was given as 20 centimeters. That's just that. So plugging all this in, mu sub naught is 4 pi times 10 to the negative 7th Tesla meters per ampere. N is 400, L is 0.2 meters, and A is 5.03 times 10 to the negative 5th square meters. Plug all that in, and you get a total inductance of 2.02 times 10 to the negative 5th henries, or 20.2 microhenries. Problem 2. If the solenoid in problem 1 has 2 amps of current going through it, how much energy does it store? Please pause the video to attempt this problem. So this is going to be another plug and chug. We can use the formula U is equal to 1/2 Li squared. The inductance was 20.2 microhenries. The current is 2 amperes. So 1/2 times 2.02 times 10 to the negative 5th henries times 2 amperes squared gives 4.04 times 10 to the negative 5th joules, or 40.4 microjoules. Problem 3. An inductor with an inductance L is equal to 4 henries is exposed to a power supply with a variable voltage given by V of t is equal to 2 volts per second times time. What is the power stored by the inductor, and what is the energy stored in that inductor, both as functions of time? You may assume that the current at time t equals 0 is 0. Please note that this problem is a little more difficult than most of the problems that I do, so please take some extra time to solve this. Please pause the video now. So the first part of this question, what is the power stored by the inductor? We want power. Power is equal to current times voltage. So voltage. Well, voltage is equal to L di dt. So we can rearrange it. We have a given voltage. Voltage is 2 volts per second times time. So we can solve di dt is equal to that voltage function divided by L, 2 volts per second times time divided by 4 henries. And that gives us a function 0.5 amperes per second squared times time. Now remember, that is the rate of change of the current, or the derivative of the current. To actually find the current, we need to apply the fundamental theorem of calculus and integrate this. So I is equal to the integral of di dt dt. or rather the change in current, but remember we said current starts at 0, so we're going to take a shortcut and say the current is equal to the integral of the derivative of current. So di dt is 0.5 amperes per second squared times time. So this is 0.5 amperes per second squared. That's a constant. We can just pull that out of the integral. But we are integrating time, and we're integrating with respect to time. So the integral of t dt, this is t to the first power, so we increase that by 1, make it t to the second power, and then divide by that 2. So we get 1/2 times 0.5 amperes per second squared times t squared, which gives us 0.25 amperes per second squared t squared. That is current as a function of time. So power is equal to current times voltage. Current we just found was 0.25 amperes per second squared t squared. And voltage is equal to 0.5 amperes per second squared times time. So we can multiply them together. Or no, voltage was 2 volts per second times time, pardon me. So we can multiply those two together, 0.25 amperes per second squared t squared times 2 volts per second t. 2 and 0.25 multiply to get 0.5. Units, amperes, and volts become watts. Second squared times second becomes second cubed. And t squared times t becomes t cubed. So the power, as a function of time, is 0.5 watts per second cubed t cubed. So the final step, find the stored energy. Now, power is the rate of change of energy with respect to time. So power is equal to du dt. So to find how much energy is stored in the capacitor, we should integrate power with respect to time. With that integral, we can say, okay, power is 0.5 watts per second squared t cubed. So integrating 0.5 watts per second squared, seconds cubed t cubed dt. 0.5 watts per second cubed, that's a constant, so we can pull that out. We're integrating t cubed dt, which we bring increase 3 to 4, and then divide by 4, so 1/4 times 0.5 watts per second cubed times t to the 4th power, or 0.125 watts per second cubed t to the 4th power. Now, this stored energy you could also have solved by taking 1/2 times the inductance times the current squared. Current squared is 0.25 amperes per second squared t squared, and inductance was 4 henries. So 1/2 times 4 henries times 0.25 amperes per second squared t squared also gives you 0.125 watts per second cubed t to the 4th power.